Computer generation of random variables. Virtually all modern technology has built into it some form of computer simulation. Everything from weather forecasting to machine learning. And such simulation requires that we be able to generate random variables with a given distribution. These distributions may be standard distributions like the exponential or the normal, or they may be non-standard distributions created for a specific task, like the distribution of claim size in an automobile insurance company. Virtually all computer software has embedded in it an algorithm for generating approximately uniform 0-1 random variables. And this is used at the heart of generators for every other distribution. So we'll assume that we're able to generate a random variable u with a uniform distribution on the interval from 0 up to 1. What we wish to do is generate a random variable capital X with a given cumulative distribution function capital F of X. And what's natural under these circumstances is to attempt to use some kind of function of the random variable u. Let's suppose first that the cumulative distribution function is continuous and strictly increasing. You'll recall from calculus that under these circumstances, capital F of X has an inverse function, denoted capital F minus 1 of y. An inverse function, f minus 1 of y, has the properties that f of f minus 1 of y is equal to y, and f minus 1 of f of x is equal to x. The function I'm going to attempt to use is f minus 1 of u. X is equal to f minus 1 of u. And let's determine what the cumulative distribution function of that random variable x is. The cumulative distribution function is the probability that capital X is less than or equal to little x, or the probability that f minus 1 of u is less than or equal to little x. And since capital F is increasing, strictly increasing and continuous, this is identical to the statement that f of f minus 1 of u is less than or equal to f of x. Because those are identical statements, they have the same probability. Now recall that f of f minus 1 of u is just u, since this is a legitimate inverse function. So we get the probability u is less than or equal to f of x. We started out with a random variable u, which was uniform on the unit interval from 0 up to 1. The probability it's in any interval is the length of that interval. So the probability it's between 0 and f of x is f of x itself, since f of x is less than 1. What we've shown is that f minus 1 of u, if we define that to be the random variable x, it has the desired cumulative distribution function f of x. We've discovered a method for producing a random variable with a given CDF, provided that cumulative distribution function is continuous and strictly increasing. The question is, what do we do if it isn't? And this requires the notion of some kind of generalized inverse or function. I'll call it f superscript minus of y. We define this generalized inverse function at the value y by looking at all the values of x for which f of x is greater than or equal to y, and picking the smallest of these, the minimum of all such x. And it turns out that this is identical to the usual notion of an inverse function, provided that f is strictly increasing and continuous. But when f of x is not possibly discontinuous or non-decreasing, it might be flat in places, then our definition of f minus produces a function which is similar to the inverse function, but doesn't satisfy exactly the same properties. Let me show you graphically how this so-called inverse works. In this picture, we have a rather strange-looking cumulative distribution function. It has jumps, and it's flat in various places, but it is, in fact, a cumulative distribution function of some kind of distribution. You'll notice that if I generated a value of y somewhere around 0.4, between 0 and 1, and I look at all the values of x which produce larger values of f of x, larger than 0.4, we get the possible x's that are displayed on this graph somewhere between 0.4 and 1. And the smallest of these is 0.4. In other words, that's the value of x that corresponds to the inverse of this y. Equivalently, a little bird flies horizontally, beginning at the value on the y-axis, until it hits the graph of the cumulative distribution function. If it hits a space, assume a window was closed at that point. It's knocked out upon hitting the CDF, and it drops vertically to the ground. That's the corresponding value of f minus of y. Of course, if we start at a value of y a little higher up, around 0.5, we end up at exactly the same point. F minus of 0.5 is still 0.4. Computer generation of random variables. The general case. Suppose we have an arbitrary cumulative distribution function f of x, and we're given a uniform random variable generated on the interval between 0 and 1. Our objective, once again, is to find a random variable x with the cumulative distribution function we prescribe, namely f of x. It turns out the solution to this is x equals f minus of u. That will have the correct cumulative distribution function, f of x. The proof is a fairly simple consequence of the fact that when u is less than f of x, strictly less, this always implies that its inverse, capital X, is less than or equal to x. And that in turn implies that u is less than or equal to f of x. This is not too difficult to see in the graph below, where you'll notice, with little x somewhere around the middle of the graph, that the values of u, strictly less than f of x, are colored yellow in this graph. And if we take the inverse function, f minus of those values of u, all of them are less than or equal to that x. Those inverses are colored green on the x-axis of this graph. So that verifies the first of these statements, that u less than f of x implies that x is less than or equal to x. The second you can check similarly from this graph. Now if we take probabilities on all three sides, we end up with an inequality that says the probability that u is less than f of x is less than or equal to the probability x is less than or equal to x. And that in turn, less than or equal to the probability u is less than or equal to f of x. What's the difference between the left side and the right side of this inequality? Both involve the probability that a uniform is in an interval. The only difference is the right side includes the endpoint, f of x. In either case, the probability is given by the length of the interval, since it's a uniform 0, 1. Both the probability u is less than f of x and the probability that u is less than or equal to f of x is exactly f of x, since f of x is something less than or equal to 1. Notice that probability x is less than or equal to x, little x, now satisfies an inequality with the same thing on the left side and the right side, namely f of x. That means it's identically equal to f of x. What we've shown is that the CDF of capital X is given by f of x. This method has generated a random variable x with the appropriate cumulative distribution function. Here's one application of this methodology to generating a random variable with an exponential distribution. We want to show that the inverse transform method results in a generator for an exponential of the form minus 1 over lambda times the logarithm of 1 minus u. Before we do that, you might notice that minus sign seems inappropriate since the exponential distribution is concentrated on the positive axis. But of course, since u is in the interval from 0 up to 1, 1 minus u is also in the interval from 0 up to 1. In particular, it's less than 1. Its logarithm is therefore negative, and so the purpose of the minus sign is to convert that negative quantity to a positive quantity. Solution. The cumulative distribution function for an exponential random variable is given by f of x equals 1 minus e to the minus lambda x for positive values of x. F of x is 0 if x is less than 0. And because f of x is continuous and strictly increasing for positive values of x, it has a legitimate inverse function as we understand it from calculus. To find the inverse, we need to solve the equation f of x equals y for the value of x. And that becomes 1 minus e to the minus lambda x equals y. Y is some number between 0 and 1. When we solve this, e to the minus lambda x equals 1 minus y. Take logarithms on both sides. Minus lambda x equals log 1 minus y. And finally, x is equal to minus 1 over lambda times the logarithm of 1 minus y. So the inverse function, f minus 1 of y, is minus 1 over lambda log 1 minus y. And the generator we're looking for is f minus 1 of u. X is equal to f minus 1 of u, or minus 1 over lambda log 1 minus u. This apparently has the appropriate exponential distribution. The exponential CDF and its inverse, in fact, any function and its inverse, have very similar looking graphs. They're displayed here, f of x and f minus 1 of x. In what sense are they similar? Recall that the inverse function is the mirror image of the original function mirrored along the diagonal. You can see that from this graph. A geometric random number generator. The purpose here is to show how inverse transform also permits us to generate random variables with a discrete distribution like the geometric. This is a particular geometric cumulative distribution function, f of x equals 1 minus 1 over 2 to the power x plus 1, where x takes an integer value, 0, 1, 2, and so on. And we've graphed the cumulative distribution function here. How does the inverse transform apply to generating a geometric random variable? Well, as always, we generate a uniform random number between 0 and 1. You can see that on the y-axis of this graph. We run across until we strike the graph, and then we drop to the floor, and that's our generated value of x. The question is, under what circumstances do we produce a given integer little x? I've displayed a certain integer x here, along with the values of f of x and f of x minus 1. The jump that occurs at the value x runs from f of x minus 1 up to f of x. U has to strike the graph in that window in order that little x be produced. In other words, in order to generate an integer x, u must lie between f of x minus 1 and f of x. That's the condition for generating an integer x. So now all we need to do is solve that inequality. We'll substitute f of x, 1 minus 1 half to the power x plus 1. This gives us an inequality. We solve that inequality carefully since it has less than signs, less than or equal to signs. For example, I multiply all three sides by minus 1 and then add 1. And because I multiplied by a negative number, I reverse the direction of the inequality. That's this line. Then I take logarithms on all three sides of the inequality. And finally, divide by minus log 2, which requires another reversal of the direction of the inequalities. And we end up with the following statement: x is less than minus log 1 minus u over log 2, which is less than or equal to x plus 1. That identifies x for us. It says that we compute the value in the middle, minus log 1 minus u over log 2, and round down to the next lowest integer to obtain the value of x. It's what's commonly called the floor of that number. Here's another problem that you should attempt on your own. Use the inverse transform method to find a random variable x which has probability density function 1 over x squared, where x is bigger than 1. Assuming, as usual, that you're given a random variable u, which has a uniform 0, 1 distribution. We begin, as usual, by first finding the cumulative distribution function of the distribution. Don't make the mistake of trying to invert the density. The cumulative distribution function is the integral from 1 up to x, f of z dz, where x is some value bigger than 1, or the integral of 1 over z squared, which is 1 minus 1 over x for x positive. And you'll notice that that's a strictly increasing and continuous function for x bigger than 1. So it has an inverse. In fact, it's easy to find that inverse. The inverse function is 1 over 1 minus y. So the generator for this distribution is x equals 1 over 1 minus u, where u is a uniform on the interval from 0 up to 1. Your last step in such a problem should always be to check that the generator produces values in the correct interval. In this case, when u is equal to 0, x is 1 over 1, which is 1. When u is equal to or approaches 1, then x approaches 1 over 0, which is infinity. So x lives in the interval between 1 and infinity. The other thing we'll note in passing is that a uniform on 0, 1, u, and 1 minus u have exactly the same distribution, both uniform on the unit interval. This means that if I wished, I could replace x equals 1 over 1 minus u by x equals 1 over u. I'll get precisely the same distribution for x. This wouldn't be exactly inverse transform, however, but it's still a generator for this distribution.